Hello and welcome to this 19th session on symmetry and chemistry. So previously we were looking at a diatomic molecule, homonuclear, oxygen, and that only involved looking at the 2p orbitals and their interaction. What we're going to do now is we're going to have a much more detailed look at diatomics. We're going to go on to consider what happens when you look at the 2s as well, when they get involved in the bonding. We're looking at nitrogen a little bit later. And fluorine is another interesting one. We have this anomalously weak fluorine-fluorine bond. But actually, to understand that, we're going to have to go into quite a bit of detail about how the energies are calculated, and that will explain our weak bond. Of course, we've looked at homonuclear diatomics, now heteronuclear diatomics, and we're going to go to carbon monoxide. Very interesting molecule, carbon monoxide, got some really unique properties. And so, for example, despite the fact that carbon is less electronegative than oxygen, we find carbon holds a formal negative charge in this molecule, and it forms extremely stable complexes with metals, which you wouldn't really expect looking at carbon monoxide. And actually, when you look at these images on the screen here, the complex there, that trigonal bipyramidal complex, this is an iron-carbonyl complex. And one thing that's quite unusual about this is that the iron is in oxidation state 0. And we'll be able to make sense of why iron is in such a low oxidation state. So that means then that we might be looking at something like a 4s2 3d6 configuration on iron, where there's 8 electrons on the iron in this outer shell. And we've got 5 of these carbon monoxide ligands. So the lone pair on the carbon is what coordinates in a carbon monoxide transition metal complexes. 5 ligands, each putting a pair of electrons in. There's a total number of electrons of 18, therefore, around the outer shell of the iron. And that's quite significant. So 18 is the number of atoms in a period, isn't it? So if you consider the 4th row of the periodic table, you've got 18 elements in that row, and so 18 electrons might be filling a shell where you've got d orbitals in there as well. Normally you think of 8 electrons in a shell, but plus 10 d orbitals will make 18. We can also see on the bottom right there, what you can see is the heme unit complex to iron and from hemoglobin. And so normally, just sitting above the iron 2 centre there, you would get an oxygen molecule bound, and so this would be obviously how the body transports oxygen around from the lungs. And this is the reason why carbon monoxide is so poisonous, because the carbon monoxide, it does form these very stable complexes with metals, which means it will irreversibly displace oxygen from its bond with iron. So this is why people get suffocated by carbon monoxide. It just displaces all the oxygen from that complex there. So, getting stuck into carbon monoxide in a bit more detail, we've got a molecular orbital diagram on the right hand side. So what's nice about this molecular orbital diagram, so provided by Geoffrey Moore in his YouTube channel, and that is that we've got energy on the y-axis. So it's nice and quantitative, this one. And so you can see we've got oxygen on the left with its 6 valence electrons in 2s and 2p, carbon on the right, so we can see there that its valence orbitals are at higher energy. This corresponds to the fact that carbon has got fewer protons than oxygen, it's less electronegative, so the carbon electrons have got more energy. And so again, this is interesting because we've got the 2s electrons involved, which we didn't have before in oxygen. We'll be looking at exactly how this works in detail later on. But one thing we can say is that the 2s and the 2pz orbitals have got the same symmetry in this C infinity V molecule, and so as a result they can interact with each other. And so you can see there that the lowest orbital, that's sigma s, this really involves the oxygen 2s bonding with the carbon 2s. And likewise, the very, very top orbital, that sigma star orbital, this is involving the oxygen 2px combining with a carbon 2px. So on these extremes, it's fairly clearly either S or P. But with the intermediate molecular orbitals, you can see that the sigma there is labelled S/P. And so this relates to the fact that the 2s and 2pz orbitals are mixing together in there. So you can see we've got a bond and an anti-bond in the middle of the picture where there's sp mixing. So they're fully symmetric, the s and the pz orbitals, given these four molecular orbitals there I was referring to. It's quite interesting that the orbital right at the bottom there, that is of similar energy to the oxygen 2s. Because the oxygen 2s atomic orbital is so much lower than the other valence orbitals, it does mean that that sigma bonding pair of electrons actually has very high oxygen character. And so essentially that's going to represent the oxygen lone pair in the molecule. As I say, we've got this intermediate character in the two middle orbitals. And in fact, this is interesting when we look at the HOMO and the LUMO. The highest occupied molecular orbital there, so looking in the diagram, the highest energy electrons there are in this sigma S/P antibonding orbital. And so these electrons there, as you can see, the energy of that orbital is kind of intermediate between the carbon 2s and carbon 2p orbitals, where it's higher than all of the oxygen valence shell orbitals. So what that's telling you is that those highest energy electrons are largely of carbon character. So these are carbon electrons which are effectively going to be the lone pair. So this is going to be the highest energy electrons in the molecule. That will be the carbon lone pair. And indeed it's going to be this electron, these electrons, as you might expect, these highest energy electrons that are going to coordinate into the transition metal when it forms a complex. So not only is the HOMO a carbon lone pair, but when we look at the diagram, the LUMO, which is the pi star, the lowest unoccupied molecular orbital, those pi star, empty pi star orbitals, these, as you can see, are very close in energy to the carbon 2p orbitals. So the LUMO also has carbon character, principally. And this is kind of the key to how carbon monoxide can be such an effective ligand, because it's going to be carbon coordinating. The carbon's going to bond to the transition metal. It provides the lone pair, which is going to form the covalent bond with the transition metal, but the carbon also is equipped with the vacant pi star LUMO orbitals, and this can do the back bonding. So that increases the bond order, if you like, of the carbon to transition metal bond. So as you can see there, the lone pairs, oxygen 2s, having very much that character in the lowest molecular orbital, that's the oxygen lone pair, the carbon lone pair being the HOMO. Having just looked at carbon monoxide, it's very interesting to make comparisons with some similar and related species, for example cyanide. And in fact, before I go further, it's worth pointing out that, of course, carbon monoxide, CO, has got the same number of electrons as nitrogen, N2. Of course, nitrogen is element number 7 electrons, so the nitrogen molecule's got 14 electrons. But carbon monoxide, of course, also has 14 electrons, except 6 on the carbon and 8 from the oxygen. So in a way, you could almost think, in carbon monoxide, if oxygen simply gave one of its electrons to carbon, that gives them 7 electrons each, which nicely work out from the point of view of overlapping to form bonds. And actually, this is what happens, isn't it? So you think, we often, as in the Lewis structure, we would draw carbon monoxide as having a triple bond, but one of those bonds would be a dative bond from oxygen to carbon. So this satisfies the octet on the carbon. But of course that dative bond will also mean oxygen formally giving and one of its electrons to carbon. So this is the origin of the carbon having a negative charge on it and the oxygen having a positive charge on it. And so in this light, it's quite interesting to compare carbon monoxide with cyanide. Because if you think about it, N minus, not that the negative charge is on nitrogen in cyanide, but if you just imagine it is for a moment, N minus would be 8 electrons, like oxygen. So Cn minus is also a 14 electron system. And actually, on the subject of 14 electron systems, carbide, where there's a carbon-carbon triple bond, if it's got a 2- charge, carbide also has 14 electrons. So we can see that these species are all related. So there you can see there carbon monoxide, cyanide, and carbide, or acetylide, or ethynide, all have 14 electrons. And so, because of course C minus, N, and O plus all have 7 electrons. And so those species there are all just different combinations of those 3 fragments. And so with cyanide, of course the negative charge is on the carbon, because of course C minus has 7 electrons, and then that would bond with N, which has 7 electrons. And so you've got 7 and 7 again with the cyanide. So in fact, the acetylide or carbide, C2 2-, this is really very similar to the nitrogen. So we could say that's isoelectronic, so the MO diagram would really look extremely similar. And likewise, cyanide will be extremely similar to carbon monoxide. Same number of electrons, heteronuclear, diatomic, so the MO diagrams will look very similar indeed. And of course, cyanide and carbon monoxide do have quite a bit in common. So cyanide, like carbon monoxide, can irreversibly displace oxygen from oxyhemoglobin. It also forms extremely stable complexes of the transition metals, which again are carbon coordinated. And so again, we see cyanide really as a kind of a champion ligand with transition metals, forming these very stable bonds. And actually on the screen there, what you can see here is a so-called hexacyanoferrate complex, where you've got 6 cyanide ligands bound to Fe2+. And this is quite an interesting one, because of course this actually is also an 18 electron complex. So because the iron is +2 there, you can say, well, it's lost its 2 4s electrons, that would leave D6. So there's 6 electrons on the iron, 2 electrons from each carbon in the 6 cyanide ligands. That's 12 electrons coming in. 12 plus 6 is 18 again. So again, that's our 18 electron complex. And so that's something that this complex has in common with the iron carbonyl one that we saw before. Both 18 electron complexes. But I mean, I can't pretend that that's the only complex that iron 2 forms with cyanide. There's also a well-known Fe3 complex with cyanide as well, I should say. And just a couple of facts about carbide. So carbide, perhaps known most famously as the salt calcium carbide, and this is famous because when it gets wet, it liberates ethine. Of course, ethine's quite a good fuel. It's quite a high energy molecule. And so there you can see there's the equation there for ethine being liberated when you get water on calcium carbide. And so beneath there we got the structure there of ethine. Right, now we're going to get stuck into some of the maths and physics that lies behind the energy calculation. And so we're going to be applying Schrodinger's equation to the orbitals on these molecules. And ultimately this should be able to make sense for us of the very weak fluorine-fluorine bond, another curiosity of the homonuclear diatomics. So there we go, we've got Schrodinger pictured on the screen there. And so this operator then, this equation, it's an operator eigenvalue equation. So the operator, so this is a beast which acts on a function to return another function, as opposed to a function which of course acts on a number to produce another number. So this operator H hat, if you like. The H stands for Hamiltonian, the total energy operator. So this operator with units of energy acts upon a wave function. And so there we go, we've got an operator acting on a function to return a different function. But in this case, it actually returns the same function, the same wave function psi, except it's multiplied by a number. This number is known as the eigenvalue E, and that E is the energy associated with that wave function. And so very often when you meet this in maths, the operator will be a matrix and the wave function will be a vector. And as it happens, of course, wave functions are often written like vectors, and these Hamiltonians are often written as matrices. So that's no coincidence. And so this is the equation in shorthand. So that little hat there on the H, that means it's an operator. So the operator acts on the wave function, that's the psi. And so it's in this kind of, this is a thing called a ket. So this is the Dirac notation we're going to refer to. So that vertical bar and the kind of greater than sign, this houses the wave function. And so as a result of operating on it by the Hamiltonian, it's going to return the same wave function, but multiplied by the eigenvalue E, the energy. But of course these wave functions are often complex, and ultimately we're going to need a real answer coming out, like an energy. So the way this is done is we pre-multiply, so we multiply from the left with the complex conjugate of the wave function. So this is the imaginary part with its sign changed. And then ultimately we integrate the whole expression over all space. So the reason why this is done is that our wave functions are defined typically so that if you multiply them by their complex conjugate and integrate them over all space, the answer is 1. This is the so-called normalization of the wave functions. And so because most of the time, or so often in this subject, you're integrating all these wave functions over all space, Dirac came up with a very neat little notation for this, which we can see here. And so he's multiplied by the left, and again he's used one of these funny kind of brackets things. So on the left hand side, that's known as a bra, and so the bra and the ket come together to form the bracket, Dirac bracket notation. And so once you kind of close off the bracket, as it were, with the bra, that implies that you're doing an integration. So we multiply by the left by the bra. We do the same thing with the E psi. But you can see past the next equal sign, can you see what we've done there is we've taken the E out of the integration. And of course you can do this because E is just a number. So as a constant we can take it outside the integral. And then, in this case, I've just said equals E. And this is because the two psi's, by implication, are the same wave function. And so that little mini bracket there with the two psi's in, of course the wave function is defined so that when you multiply it by its complex conjugate and integrate it over all space, the answer is 1. So that psi bracket there ends up collapsing to 1, and that's why it all just ends up as E. And so we've succeeded then in finding the energy of a wave function. Now if you've got two different wave functions in the integral, then that's a different kettle of fish. We can't then say that the psi star psi is necessarily going to come to 1. And so what you'll be actually finding in this time is an interaction energy between two different orbitals, or two different wave functions, A and B in this particular case. But the point has to be made that energy is scalar, because energy is just a number, it's not a vector. It has to be therefore fully symmetric. And so because ultimately our energy has to be fully symmetric, the two wave functions involved have to have the same symmetry, because the whole integral has got to have a fully symmetric result. So if the operator is fully symmetric, the only way the whole integral can come out as fully symmetric is if the two wave functions have the same symmetry. So this is one of the things we found before, is that the product of, or like the square as it were, that direct product of two symmetries that are the same, that's the only way you get a fully symmetrical result. And then because we've got loads of these integrals, yes, it's a nice bit of simplification to use the Dirac notation, but actually we abbreviate it even further because we're going to get some quite long complicated expressions to deal with. And so ultimately, these Hamiltonian integrals, if they're between two identical wave functions, they're called alpha terms. And so, of course, if the two wave functions are identical, then what you're finding is simply the energy of that wave function. And so alpha here represents the energy of a particular wave function. But if the two wave functions are different, A and B, then that integral then is called beta. And so this would be the interaction energy between two different wave functions. Of course, they'd have to be two different wave functions of the same symmetry to have an interaction energy. And so just finally there, a reminder that this psi star psi integral ultimately is going to come to 1 for a single wave function and its complex conjugate, because of the way these wave functions are normalized. So this is why normalization is such a useful thing, because of course all these integrals can then just be, cancelled to 1 in these cases. Now if the integral has got two different wave functions involved, then we're going to have to work out what that result is. And so this kind of integral is called S, the so-called overlap integral between two different wave functions. And so S is the abbreviation that we use for that sort of integral between two different wave functions. Now we're going to put the Schrodinger's equation into practice. And really the first thing I should say is that the wave function psi actually holds all the orbitals under consideration in our problem. So for example, it could hold all the atomic orbitals in a problem. It may indeed hold a symmetry adapted linear combination of orbitals. And when we look at this quantity psi h hat psi, ultimately we've got to consider the combination of all the possible atomic orbitals from the ket on the right hand side and the bra on the left hand side. So this can be very complicated. So starting with the simplest possible example would be just looking at the 1s orbitals on each H atom in a hydrogen molecule. So we could label the H atoms HA and HB, and in doing so we've got 4 possible combinations of orbitals: AA, AB, BA and BB. And so we're going to slightly rearrange the Schrodinger equation now. So rather than H psi equals E psi, we'll write H psi minus E psi equals 0. It'll be mathematically useful to do it that way. And in fact we're going to abbreviate it where the different orbital components of the wave function are going to be in these kind of subscripts. So you can see I've got H hat ij minus E S ij equals 0. So the I and the j, these indices, are going to be summing over the orbital components in the bra and the orbital components in the ket. So the I label, for example, might be counting over the atomic orbitals that make up the bra wave function, and the j indices could be summing over all the atomic orbitals in the ket wave function. And so we're going to do some further abbreviations. So HAA will be equal to HBB, because this is just going to be the energy of the 1s orbital on the hydrogen atom, and so this just gets simplified to alpha, just the orbital energy. But these cross terms HAB, well, HAB will equal HBA, and we're just going to abbreviate that to beta. It's the interaction energy. Then the overlap integrals, SAA equals SBB equals 1, because the wave functions are normalized. And we're going to say SAB equals SBA, and we'll just call that S. It's the overlap integral. And so what we get actually are these 4 equations relating to the 4 sets of indices. And so I, this can correspond to the atomic orbital in the bra psi, and J can correspond to the atomic orbital in the ket psi. And so actually what we can do is we solve these equations simultaneously, bearing in mind these different indices counting over orbitals in the bra and the ket, ultimately by creating a so-called secular determinant. So it's a square determinant which corresponds to the 4 equations we're solving simultaneously. And we can do this because we write all our equations as equal to 0. And so they'll all solve simultaneously when the secular determinant equals 0. And so you can see there we've got alpha minus E on the diagonals. So remember, the diagonal terms are connecting the same orbitals, which is why the S equals 1. and then beta minus ES for these off-diagonal terms, where we've got S for the overlap integral. And so what we're going to do now, we're going to make a bit of an approximation to make life easier. So this overlap integral, normally fairly small, we'll approximate it to 0. And so that means that the off-diagonal terms will just be equal to beta, and that makes life a bit easier for us. And then we solve the determinant, so reading across the rows, if we call each of these elements A, B, C and D, then the determinant is AD minus BC equals 0, which we're setting to 0. So in other words, alpha minus E all squared will equal beta squared. So when we square root that, that'll give us alpha minus E equals plus or minus beta. And so rearranging, that gives us the solution for the energy as alpha plus or minus beta. In other words, there are two solutions for the energy. And this really highlights the fact that our Hamiltonian operator ultimately is expressing an interaction which is going to lead to two different energy levels. So just remember that alpha here, this is going to be the non-bonding atomic orbital energy of the 1s. Beta is the interaction energy. Beta is actually a negative quantity. And so these solutions, alpha plus or minus beta, well actually the plus term, alpha plus beta, because beta is negative, that's actually going to be the lowest energy solution. And so this is the bond energy. And so alpha minus beta there, that's going to be the anti-bonding energy solution. So that's beta either side of the non-bonding atomic orbital energy, alpha, which incidentally is also a negative quantity because it's relative to the 0 in energy at the ionization limit. So now we're going to take this a little bit further. We can see on the screen that we've got a molecular orbital diagram for hydrogen atoms A and B. And so on the left hand side, also on the extremes there, where we have just the 1s orbital, this is the hydrogen 1s in a sort of non-bonding state, in that sort of average energy. And then we have the dotted lines there, connect them to the molecular orbitals. So you can see these are in the middle as usual. And so we have the lower energy being the bond, accepting both of the electrons, and the higher energy antibond. And the picture we may have in our mind is this idea of wave constructive and destructive interference, of wave interference. So if we think about the orbitals as standing waves, so when the standing waves superpose, we can think of them as having a constructive and a destructive possibility. And so where they constructively interfere, that gives you the bonding orbital. Where they destructively interfere, it gives you the antibonding orbital. So the kind of logic of this is that where there's constructive interference, the wave amplitudes add together to give you a significant amplitude between two nuclei, and this is where the bonding electrons live. But where there's destructive interference, you get cancellation to 0 between the two nuclei, leaving the only electron density on the far sides of the nuclei. And so then, with no electron density between the nuclei, all the nuclei experience really is repulsion from the other nucleus effectively. And so that causes them to spring apart, which is what the antibond does, it breaks the bond. And so of course the antibond, with this 0 of electron density between the nuclei, that represents a nodal plane. So this is a kind of intuitive physical picture that we tend to have when we work with orbitals. And I just wanted to make the point actually that we can derive all this quite nicely from group theory. So in the case of the hydrogen molecule, of course this is d infinity h symmetry, we can create a representation for the two 1s orbitals in this symmetry. And so what I've got here is a little character table where at the bottom row there, this is the representation of the two 1s orbitals, which is why you have a character of 2 for the identity. And so when you're rotating the orbitals around the molecular axis, obviously being s orbitals, they don't change at all. So you get 2's coming as the character, essentially for the rotations and also the reflections in the vertical planes, which hold the principal axis. And then, of course, when it comes to reflecting in the perpendicular plane to the principal axis, of course, that moves the 1s orbitals off their positions, and so that involves zeros for the characters for the remaining operations that all involve moving them, either reflecting them in that plane or with these C2 prime. These are the perpendicular C2 orbitals, that C2 axes that just rotate the orbital from one end of the molecule to the other. So that representation that we've got there, 2, 2, 2, 2, 0, 0, 0, when we reduce this into the irreps in d infinity h, this then returns to us these two sigma orbitals, sigma plus g, sigma plus u. Of course, we tend to use capital Greek letters in the character tables. We tend to use lowercase Greek letters when it comes to labelling the orbitals in molecules. And so these are your sigma bond and your sigma antibond. And so the fully symmetric sigma g, this is going to be our bond, where you've just got the lobe in between the two nuclei. And the antibond, on the other hand, where you've subtracted one from the other, and you've got lobes of opposite phase either side of the nuclei. So these are our two molecular orbitals, and when it comes to the fully symmetric ground state, that's fairly obviously just the sum of the symmetry adapted linear combination is clearly just the sum of the 1s orbitals on each atom, and the 1 over root 2 there just normalizes it. And it's kind of obvious really, I suppose, what the SALC is going to be for the antibonding orbital, but if you want to go through with it, what you can do is you can simply do the same thing we did before, where you kind of project the irrep onto one of the orbitals and sort of construct the symmetry adapted linear combination. So it's not exactly obvious how you're going to do that when you've got infinite numbers of operations like this, but I think there is a kind of way you can think yourself through it, because when you look at the character table, you've basically got an infinite number of rotations and an infinite number of sigma v reflections. So it's a bit like two lots of infinity operations that have a +1 character. But at the same token, you've got an infinite number of improper rotations, that's these S operations, and you've got an infinite number of C2 prime axes, which take one orbital onto the other orbital's position. So again, you've got like two lots of infinity, which in the case of the sigma plus u irrep, so this is our antibonding irrep, you've got negative characters, you've got -1 character for all those operations. So you've got sort of two infinities worth of +1 character and two infinities worth of -1 character. And then given that the improper rotations and C2 prime axes move, if you like, HA onto HB, then ultimately when you go through this process, given the kind of equal numbers of operations that go either way in the -1 character, ultimately it's going to simplify to 1SA minus 1SB. So that's a kind of group theory justification for the symmetry adapted linear combination of the antibonding orbital, which of course makes perfect sense from our sort of physical intuitive picture. Right, now finally, after all that work, we should be in a position to explain the weak fluorine-fluorine bond. So up on the screen here we've got the fluorine molecular orbital diagram. So you can see it looks just like the oxygen molecular orbital diagram, but the difference is though we've got another couple of electrons. And so one thing that's special about fluorine that makes a big difference here is that even though there's only nominally bond order 1 in the molecule, there are an awful lot of pairs of electrons. So in actual fact we've got, in this molecule, we've got 3 antibonds, haven't we? We've got a sigma star and 2 pi star antibonds. And we've got 4 bonds, 2 sigmas and 2 pi's. So we've got 4 bonds and 3 antibonds, leading to an overall bond order of 1. And it's quite significant having a large number of antibonds, because what we're going to discover now, using the energy calculations we've been working with, is that it turns out that the antibond is slightly more antibonding than the bonding is bonding. And so we'll justify that now. So as I say, these occupied antibonding orbitals, and it's going to come down to the denominator in a molecular orbital energy expression. So what we need to do here is we need to actually do the same thing we did before, solving for our 2 by 2 determinant, But now we're not going to make the approximation that S is approximately 0, the overlap integral. So that makes it slightly harder work for us, but it is going to be physically relevant because, of course, the overlap between orbitals is going to be more significant in fluorine than it is for other atoms in that period, because the bond order is because the bond length is so short. So you know the atomic radius of atoms shrink as you go from left to right across the period. So we've got a very short bond, and so we can have quite a significant, I think, overlap between the orbitals. And so, again, as I say, we're not going to approximate S to 0. So when we look to solve our determinant here, essentially that's going to be alpha minus E all squared. It's going to equal beta minus ES all squared. So when we square root that, alpha minus E will have to be plus or minus beta minus ES. Now we want to solve for the energy. We want to know what the energies are. So what we do is we collect terms together where we've got the energies. So I've got energy there in front of a bracket, but we've collected up the energy terms together. And so if you make energy the subject, you get this expression, which is very important. Alpha plus or minus beta, 1 plus or minus S, the overlap integral. And so, as before, we've got two possible solutions for energy. We've got the plus combination there and the minus combination. And so, again, just to remind you, as we saw before, the energies alpha and beta, these are all negative quantities. S, though, the overlap integral, S has to be between 0 and 1. So, of course, you can't get better overlap than when you've got two identical orbitals. That's perfect overlap, and that's the normalization of the wave function. It's defined to be 1. So you can't exceed that amount of overlap. And so the overlap has to be between 0 and 1. And so we look at these two terms, the positive term, the E plus and the E minus, if you like, whether or not you take the positive or negative in that expression for the energy. And so when you have the positive term, alpha plus beta over 1 plus S, of course, remembering that beta is a negative quantity, and remembering that the bond is going to be the lowest energy of the two, then alpha plus beta over 1 plus S is the bond, and so alpha minus beta over 1 minus S is the antibond. So it looks like the expression we saw before, except last time we didn't have the denominator, and the denominator is going to make all the difference here, because of course S is a positive number. So you can see here that in our bond, the denominator is going to be a little bit bigger than 1, and in the antibond, the denominator is going to be a bit smaller than 1. And so, of course, when you've got a denominator in an antibond that's smaller than 1, that kind of blows up the whole fraction. So this explains why the antibonding orbital is further above alpha, the non-bonding energy, than the bonding orbital is beneath alpha. So it shows you here that, as I say, we normally draw these MO diagrams so the bond and the antibond kind of look symmetrical in energy either side of the atomic orbitals, and it is approximately symmetrical, but it's not exactly symmetrical. And where it's not symmetrical, the antibonding is more antibonding than the bonding is bonding. And actually that kind of makes sense in a way, because if you think about it, like for example, if you had a molecule like dihelium, He2, of course, if you had the two 1s orbitals from hydrogen overlapping to give you a bond and an antibond, if you've got 4 electrons going in, 2 from each helium, you would simply fill the bond, fill the antibond, and so we'd say that gives you a bond order of 0. But you could say that, well, can't a bond order of 0 just be in equilibrium with 2 unbonded H atoms, which is also a bond order of 0, He atoms, I should say. But of course, in helium, we only see it as monatomic. We don't see any diatomic helium, and so that is kind of consistent with the antibond being more antibonding, because of course if you then try to put an He2 molecule together, once you take into account the antibonding orbitals are more antibonding, you see then the total energy of the He2 molecule, the total energy is greater than having 2 unbonded atoms, which would explain why we don't see any He2 molecules in equilibrium. And so, as I say, with the fluorine, we've got these 2 antibonds. We've got 3 antibonds in the molecule, and of course those 3 antibonds are all going to be a little bit more antibonding than the bonding is bonding. We've got a significant overlap integral with it being fluorine, and so this ultimately adds up to slightly diminishing the bond order, as it were, from being like a perfect integer 1, and that explains the surprisingly weak FF bond. So when you go up the halogens, iodine, bromine, chlorine, fluorine, as you go up the halogens, the bond gets shorter and the bond gets stronger, going iodine to bromine to chlorine, and then fluorine breaks that trend. So the fluorine bond is actually weaker than the chlorine bond, despite being much shorter, and it's because of these overlap and anti-bonding effects. Now, getting slightly more technical now, because what we're going to see next, we're going to try and make sense of the slightly odd MO diagram that we see in nitrogen. And this is because we need to consider the effect of the 2s orbitals with the 2p. And actually with a carbon monoxide molecule, that did give us a bit of an insight into the fact we get mixing between 2s and 2p, specifically 2s and 2pz. And the reason is because they got the same symmetry. So as we said, with the sort of Hamiltonian operator, because it's fully symmetric operator, it has energy, it creates these interaction energies between orbitals of the same symmetry. And so normally this is just identical orbitals, but of course we can also have different orbitals, different energies, but the same symmetry. And this is what happens when you have S and say 2pz interacting in an MO diagram. And so what we can do is we're going to work through our calculation again, but this time the two atoms, which we called A and B, rather than being two identical hydrogen atoms, they're now going to be different. And so in fact, just looking at this generally between two orbitals in the abstract, rather than necessarily being different atoms, but just looking at two orbitals in the abstract, we're going to have different energies. So A and B are not going to be the same. But just to keep life simple, we are again going to approximate the overlap integral to 0. Okay, so you can see in our determinant up there, instead of just alpha minus E on the leading diagonal, we've got two types of alpha. Alpha of orbital A and alpha of orbital B. And beta is the interaction term between them. And so when we solve our determinant, now it's these two bracketed terms, alpha A minus E and alpha B minus E, these are now going to equal beta squared. And so, like we did before, we need to get an expression in terms of E, but what makes life a bit more difficult for us now is that with these two different types of alpha, we're actually going to end up with a quadratic in E. So I've just rearranged the equations to have terms in E squared, E and a constant equal to 0. And so what we're going to have to do in a minute is we're going to have to assume, we just have to make an arbitrary decision about which alpha is bigger than the other. So we're just going to assume that alpha for orbital B is greater than alpha for orbital A. It's just a random choice. So here's the solution to our quadratic. So as you know, it's like minus B plus minus B squared minus 4AC. And so the B here is minus alpha A plus alpha B, so we get rid of the minus sign. Then we've got the square root of B squared minus 4AC. And quite interesting, if you look under the square root sign, we've got alpha A plus alpha B all squared minus 4 alpha A alpha B. So because if you open up the alpha, if you expand out alpha A plus alpha B squared, that gives you plus 2 alpha A alpha B. But then when you subtract 4 alpha A alpha B, that leaves you with alpha A squared plus alpha B squared minus 2 alpha A alpha B, and that of course is the same thing as alpha B minus alpha A all squared. Now of course we could have chosen to do alpha A minus alpha B all squared, but we've just made this arbitrary decision that alpha B is larger than alpha A, so we write it that way just to keep it positive, plus 4B squared. So how on earth are we going to solve this? Well, we're going to have to start making some more approximations. And so the next approximation we're going to make is going to be using the binomial expansion. So this little trick that we do here, so we can use the binomial expansion, is under the square root sign, you could multiply everything by alpha B minus alpha A all squared divided by alpha B minus alpha A all squared. So that's just multiplying everything by 1, which is fair enough. But what we're going to do, the alpha B minus alpha A all squared, if that's underneath the square root sign, we can take it out and call it just alpha b minus alpha a. And so we then put that in front of the square root, which you can see in that first term on the left. But the denominator, the alpha b minus alpha a all squared, that cancels the first term to 1, and then it becomes the denominator underneath 4b squared. So that's quite a nice little bit of algebra, because then we can use this binomial expansion where 1 plus x square rooted is approximately equal to 1 plus a half x. Obviously that's truncating quite early the series, but it's quite a convenient approximation to make. And so the square root then disappears, and it just becomes 1 plus a half of 4b squared over alpha b minus alpha a all squared. So that's the second step you can see there on that line. And so having created the expression like that, we're now in a position to say what the solution is. So for example, if we take the solution and we take the positive from the plus or minus there, then you can see there that the alpha a is going to cancel, and that just leaves us with alpha b plus, and you can see that the alpha b minus alpha a all squared denominator, you can see one of those products of brackets, one of those brackets is going to cancel. And so we're going to end up with the positive term will be alpha b plus or minus plus b squared over alpha b minus alpha a. So you remember here that alpha b was higher in energy, and then b squared, of course beta is a negative term, but beta squared is positive, and alpha b minus alpha a is also positive because we've decided that alpha b is larger than alpha a. So what's happened here is that in this interaction, the higher energy orbital b has gone even higher in energy. So it's alpha b plus a positive term. And then when we look at the alpha minus solution, so you can see in this case the alpha b's are going to cancel. The E minus solution is going to give us alpha a. So this was the lower energy orbital. So the lower energy orbital then goes down even lower in energy by beta squared over alpha b minus alpha a. So again, there has to be a positive quantity. So basically, these two orbitals we've started with, A and B, are separated in energy, and after this interaction, they become even more separated in energy. And so this is a common principle that whenever two orbitals interact, if the orbitals are equal in energy, they end up dividing into a lower energy bond and a higher energy antibond. If the orbitals are already separated in energy, they separate even more to go to an even lower energy bond and an even higher energy antibond. And so this is the reason when you can you might come across a thing called correlation diagrams, where you look at how orbital energies vary depending on, for example, nuclear coordinates. And so one thing you see is that orbitals of the same symmetry can never cross, and that's because as they interact, of course, they always get more separated in energy. And so we can now use this result and apply it ultimately to our MO diagram. Oh yeah, the other point to make about this, first of all, this picture to make sense, we've got to assume that the difference between the orbital energies A and B has got to be significant. It's got to be significantly larger than beta, the interaction energy. So in other words, the A and B are like widely separated, and they just get like tweaked, so they're just a little bit further separated. Also, if you look at the interaction term, beta squared over alpha b minus alpha a, we need a decently sized alpha b minus alpha a on the denominator, because that whole second term's got to be quite small compared to the alpha b and the alpha a. And the other significant thing about it is that with the alpha b minus alpha a on the denominator, what that's telling you is that the interaction energy is going to get smaller with the difference in energy between the two orbitals that are involved, that are interacting. And of course this is something that we kind of almost take for granted, that you see the greatest interaction between orbitals of very similar energy, and as they get more and more different in energy, we see smaller and smaller interaction. So this really was why we neglected, for example, 1s orbitals when we're looking in the second shell, because it's just way off in terms of energy, and orbitals that are very different distance in energy, we end up neglecting them. And this is basically why we neglect them, because the interaction energy has got the difference in orbital energy on the denominator, So when they're very different, then you get negligible interaction. And that's why these orbitals that are very different energy are often just considered to be non-bonding orbitals. And so finally now we get to our molecular orbital diagram. So here we see an MO diagram for nitrogen, which looks a bit different to oxygen. It's a bit less tidy. And so you can see here there's a bit of overlap going on between the 2s and 2p in the molecular orbitals. And so just kind of reiterating this point, when we were looking at the oxygen case, we only considered the 3 2p orbitals at the top, just giving us a sigma and 2 pi's. But now, in the case of nitrogen, we're also mixing the 2 s's in there as well. And so when we had the 3 2p orbitals on each atom interacting, we got a total of 6 molecular orbitals out. But all 6 of those orbitals had different irreps. Well, I suppose we need to consider the pi's as pairs. But essentially we had 4 different symmetries. We had 2 sigma symmetries and 2 pi symmetries. All the symmetries were different. So there was no scope for having more than one MO of the same symmetry. But that's different when it comes to this nitrogen case where we've got the 2s in there as well. Because remember, 2s and 2pz have got the same symmetry. And in the MO diagram, they're both going to produce sigma u and sigma g bonding and anti-bonding orbitals. And so in the MO diagram, you've got multiple orbitals that have got the same symmetry. And so you start getting this interaction energy that we were just deriving in the previous slide coming into play. And so this effectively is mixing, because this interaction energy mixes the 2 orbitals together. And so what's most significant here is the sigma bonding orbital from the 2p overlap, because in the case of oxygen, that sigma bond was lower in energy than the 2 pi bonds. But you can see it's flipped over here, and this again is from the mixing. And for this to happen, of course, remember we were saying that we don't want the energy between the orbitals to be too great to see this mixing. And of course this is the significant thing, because as you go left of oxygen in the periodic table, you've got fewer and fewer protons in the nucleus, and with fewer protons in the nucleus you get less separation between the 2s and the 2p orbitals. So with carbon and nitrogen, for example, there's not that much separation between 2s and 2p, and you see this mixing. But when you get to oxygen and fluorine, there's more separation, and even though there's some mixing in principle, it doesn't really make a big difference to the MO diagram. So this is where, so nitrogen to oxygen, this is the kind of the divide in the case of whether or not you see the mixing. And so, as we said before, when you've got orbitals of the same symmetry, their interaction causes them to further separate. So for example, the sigma bond between the 2p orbitals, the 2pz orbitals, that is going to be interacting with the sigma bond between the 2s orbitals. And that will cause the 2s sigma bond to go down and the 2p sigma bond to go up. In other words, it's like they're repelling each other, they're moving away from each other. And in the case of nitrogen, that interaction is strong enough that the sigma from the 2p orbitals actually goes over the pi orbital energy. So you get this reversal of energies. And so, yeah, it's just the final bullet point there. So this is what lies behind this slightly peculiar looking switch over in the MO diagram for nitrogen. And of course we'd expect to see exactly the same thing in the carbide MO diagram, perhaps even more so, as carbon is to the left of nitrogen in the periodic table.